Hi, I'm Wanrong from Georgia Tech, and I'll be talking about attribute privacy framework and mechanisms. And this is a joint work with Olga Ohrimenko, she's at University of Melbourne, and my advisor, Rachel Cummings, she's at Columbia University. Attribute privacy protects the global properties of sensitive attributes in a dataset from leaking during analysis. So for those of you who are familiar with differential privacy, we are used to thinking about privacy at the individual level, corresponding to roles of a database. And we ask questions of the form. What can an adversary learn about Alice data based on an analysis of this dataset? And in this work, we instead consider privacy of the attributes or columns of a database. Then is we take the view of a database owner who wishes to publish aggregate statistics about her database, and must also protect protect privacy of the aggregate information in certain sensitive columns. In this example, the owner may wish to publish average SAT score of its students, and let's assume that's non-sensitive information. However, we know that SAT score are correlated with some sensitive attributes such as race, gender, and socioeconomic status. So even though the SAT score column is not sensitive, privacy protection is still needed to prevent leakage of these other attributes. There are a few other use cases for attribute privacy. For example, hospitals want to share the number of COVID cases with federal health agencies, but want to protect mortality rates that may affect future funding opportunities. Companies want to share client data, for example, for standardization, but want to protect proprietary information. And researchers providing data for reproducibility in peer review process, but don't want other researchers to perform some new analysis on the data. In general, attribute privacy concerned about sharing aggregate statistics of a dataset, but want to protect other aggregate properties which may be correlated with the shared information. Several recent literature shows that such global properties about the dataset can be leaked even when removing the sensitive attribute. Also, models with adversarial learning, such as disentangled representations, has also been shown inefficient even to protect individual level attribute privacy. And differential privacy can only be used to protect sensitive attributes at the individual level. So the study of attribute privacy at the global level is still limited in terms of framework for reasoning about it and mechanisms for protecting it. So first, I'm going to talk about the formal framework and definitions. Our formal definitions of attribute privacy are based on this pufferfish privacy framework. The pufferfish privacy generalizes differential privacy in two ways. It allows the analyst to specify distribution knowledge about where the data came from, and domain knowledge about what should be kept private. It also can accommodate correlated data, where the correlation was across rows. The pufferfish framework has three components: a set of secret S, then there's a set of possible facts about the database we wish to hide, and a set of discriminative pairs. Then there's pairs of secrets we wish to be indistinguishable. And the class of data distributions, data then captures conservative assumptions about the underlying distribution, then generates the database. And formally, we see a mechanism is epsilon delta pufferfish private in a framework SQ data if for all possible data distributions, then in this class, and for all secret pairs with non-zero probabilities, and for all possible subset of outcomes. The probability of the outcomes conditioned on the secret pairs should be closed in this epsilon delta closeness notion, similar to differential privacy. So we first introduce a data model for attribute privacy. A dataset X contains n records, each with m attributes, and each record is sampled ID from an unknown distribution D, where attributes within a record may be correlated. And xi is the ith column vector of X corresponding to the ith attribute. And xij is the ith attribute value of the jth attribute, jth record. And C denotes the indices of sensitive attributes that require privacy protection. And the goal is to evaluate a function f on the dataset X and release f of X while protecting some information about the sensitive attributes. And we introduce two notions of attribute privacy. Before we make those definitions formal, we'll start by distinguishing them. The first one is dataset attribute privacy, which protects the attributes of a particular dataset. And the property of the attribute is modeled by this function gi of xi for a particular column. For example, the property could be, was there more Caucasians or Asians present in the dataset? Our second privacy notion is distributional attribute privacy, which protects the parameters of the underlying distribution from which the dataset was sampled. For example, the property could be, were there more Caucasians or Asians present in the population than was sampled to create this dataset? You may wonder, wait, aren't they the same? Well, they are almost the same in the above case, since GIXI is an estimate of phi I. But this distinction is important when guaranteeing privacy for unlikely realizations of the dataset, such as the maximum or minimum, or when n is small and GIXI is a poor estimate. Here's our formal notion of dataset attribute privacy. For our data model that we talked about earlier, and for each attribute I, that GIXI models the aggregate information about a particular sensitive attribute, and its codomain is UI. We formalize our dataset attribute privacy definitions using the pufferfish privacy framework by specifying the three components. The S is a set of secrets, and a secret is the event that GIXI takes values in a certain set. And S includes all secrets for all protected attributes, and it could include all subsets or only certain events. And Q is a set of secret pairs, and it includes all pairs of secrets on the same sensitive attribute. The pufferfish framework considers distribution over the entire dataset X, but we consider distributions over records. So we resolve this by defining theta to be the allowable distribution, to be the collection of distributions over the dataset then induced by the allowable ID distributions over records. The distributional attribute privacy is a bit tricky. Let Xij be the data record sampled from unknown distribution described by a vector parameter phi. And the main idea is we define the secrets to be the attribute-specific random variable phi I to be the marginal distribution of Xij conditioned on the value of all other phi k fixed. Although it seems natural for phi I to define the marginal distribution of the S attributes, this wouldn't capture the correlation across attributes that we wish to study. Instead, this phi I defines the conditional marginal distribution of the S attributes, given all other phi k fixed, which does capture such correlation. And this also allows the distribution over the dataset to be fully specified given phi and the size of the database N. Then our instantiation of the pufferfish framework is very similar to the previous definition, with this attribute-specific random variable phi I taking place of the attribute-specific function gi(xi), and the data is described by phi and n. And given the notions of attribute privacy, we also have three mechanisms to achieve that. We propose a variant of the differentially private Gaussian mechanism. It satisfies epsilon delta dataset attribute privacy when f of x conditioned on gi(xi) is Gaussian. We also relax this assumption and extend them to handle non-Gaussian data in the paper. And I'll talk about the main point in 2 slides. So the differentially private Gaussian mechanism computes the true answer f of x and adds mean zero Gaussian noise with variance that depends on the sensitivity of f, which is the maximum change in the value of f caused by changing one row of x. And the attribute private Gaussian mechanism does the same. But now we need to have a new definition of the sensitivity. And here is our definition of sensitivity of f with respect to the x attribute. And this differs from the sensitivity notion used in differential privacy in 2 key ways. First, we're concerned with measuring changes to the value of f caused by changing secrets corresponding to the realizations of gi(xi), rather than by changing the individual's data. And second, we assume our data are drawn from an unknown underlying distribution data. So this f of x is a random variable. And our attribute privacy sensitivity bounds the maximum change in posterior expected value of f of x in the worst case over all distributions and the pairs of secrets for each attribute. And in the case that if f of x is independent of the protected attribute xi, then the sensitivity is just 0, and no additional noise is needed for privacy. Here is the attribute private Gaussian mechanism. It takes a dataset X, query F, the sensitive attribute index is C, and the corresponding secret function gi, and the framework SQ theta and privacy parameters epsilon and delta as the input. Then the scale of the noise to add for privacy, this sigma square depends on the sensitivity of the query. And this variance of the conditional distribution of f of x given gi(xi) can be discounted. Then if the sigma square is positive, it will sample noise to mask some correlation among attributes. Otherwise, it won't add noise. It means privacy comes for free when f of x has low correlations with gi(xi). A natural question is how we can apply the Gaussian mechanism when the distributional assumption doesn't apply. And our idea is based on using a collection of Gaussian distributions to approximate the actual distribution. We quantify this distributional closeness using approximate max divergence. Then the mechanism still satisfies epsilon delta dataset attribute privacy, where this epsilon and delta depend on the approximate max divergence between the actual distribution and the Gaussian approximation. The second mechanism is a Markov quilt mechanism. It satisfies epsilon zero distributional attribute privacy, where the attributes can form a Bayesian network. We base our mechanism on the idea of a Markov quilt, which partitions a network of the correlated random variables into those which are near a particular variable xi and those which are remote. So intuitively, we will use this to partition attributes into those which are highly correlated with our sensitive attributes, denoted xn, and those which are only weakly correlated, denoted xr. For example, in this Bayesian network, for the family income, when we use gender as a Markov code, then the income and the SAT score would be the nearby attributes, and the height and the weight would be the remote attributes. Then we need to measure how much our sensitive attribute depends on a set of attribute parameters phi a, and how much changing the value of a set of columns xa changes the value of f. So we quantify the effect, then changing the distribution parameter phi I of a sensitive attribute xi has on a set of attribute xa using the max influence, and this max influence is based on the distribution parameter phi, and this is sufficient because attributes are mutually independent conditioned the vector of phi. The sensitivity of f with respect to a set of attribute A, denoted delta AF, is defined as a maximum change than the value of f caused by changing all columns XA. We see the two databases X and X prime are A column neighbors if they are identical except for the columns corresponding to the attribute A, which may be arbitrarily different. So this is the attribute private Markov quilt mechanism. And at a high level, we add noise to the output of f scaled based on the sensitivity of f. We only need to consider the influence of the nearby attributes then using f, and this allows less noise to be added. And in some cases, if the query f is about attributes that are all in the remote set, and the max influence on the corresponding Markov quilt is less than the privacy parameter epsilon, then no noise is added. So privacy comes for free again. Now we've introduced the attribute private Gaussian mechanism and the attribute private Markov quilt mechanism. We also have an attribute private Wasserstein mechanism, and this Wasserstein mechanism is proposed for the general pufferfish framework, so it can also be applied here, but it's computationally inefficient. As a conclusion, in this work, we introduce the dataset attribute privacy and distributional attribute privacy to protect attribute privacy of data, rather than privacy of individuals. We show that pufferfish framework can be instantiated to accommodate correlations across columns, which is needed for attribute privacy. We also provide 3 mechanisms for satisfying attribute privacy. As we mentioned at the beginning of this talk, attribute privacy has many applications. Future work includes applying and adapting these tools to relevant applications for domain experts. And for more details, please check our paper online, and thank you.